In this lecture, we start to address even more complicated models that have increasingly large numbers of parameters. And so to start to think about this, we look at now the relationship between Pseudomonas and time in our data set that was introduced in the previous mini lecture. So here, again, we have time, so study day on the x-axis. And now this is the qPCR data giving us the absolute abundance of Pseudomonas, the second pathogen. So Burkholderia in the previous lecture was one pathogen. This is Pseudomonas, another pathogen that is also an antibiotic-resistant pathogen that's increasing over time. But while the relationship between Burkholderia and sample days was clearly linear, this is less obviously linear. In fact, it looks like it's some kind of saturating function. Right? So if we fit a line here, there is a region of the data which seems to not be on the regression line. So if we use our usual QQ norm statistics, we see this deviation that's here. Now, interestingly, this deviation is not statistically significant. So if we use the KS test with respect to normality, we don't get we fail to reject the null hypothesis that the distribution is not normal. But nonetheless, there is a systematic pattern, a systematic deviation from normality. So it would not be incorrect to simply ignore this deviation from normality and push ahead with our linear models. But we're going to explore another alternative that tries to increase the number of parameters in the model to deal with the nonlinearity of the model. So again, one solution would be just to ignore the deviation from linearity and just proceed as normal. We could remove the interaction terms. So remember in the previous model, we had an 8-parameter model and a 5-parameter model. So this is exactly analogous to the previous mini lecture. Just as in the previous mini lecture, the difference between the 5-parameter model and the 8-parameter model, that is to say with the interaction terms, was not significant. So we could go down to a 5-parameter model. The 5-parameter model seems fine. If we just look at the 5-parameter model and look at the deviations from linearity, it seems fine. So this, or the deviations from normality, it seems fine. We could just go ahead with the 5-parameter model as we did with the Burkholderia data. And likewise, the treatment categories here. So in the Burkholderia data, the treatment, only one of these three individual dummy variables was significantly different from the treatment background. Here, all three of them are. So we could again report that. So again, it's in the ballpark when we graph this out. So this red line represents our treatment variable here. And then remember that in our 5-parameter model, the slope is, there's only one slope. So all 4 of our regression lines representing the different categories are all four of the regression categories have the same slope. The null hypothesis is that the intercept is different. This shows the intercept that is the best fit for all of these data. And clearly here, the treatment, so remember treatment is during antibiotics, it's more clear with the Pseudomonas data than with the Burkholderia data that the treatment was depressed relative to the other time points. So you can see the red dots here are well below the other time points, although this is perhaps being driven by some outliers in these sample days. So the data here are more consistent for Pseudomonas than they were for Burkholderia. We could have a biological interpretation of this data set that the antibiotics seem to be, the Pseudomonas seem to be responding more to the antibiotics than did the Burkholderia because we have a significant difference. This red line here for the antibiotics is lower than it was relative to the other data sets for Pseudomonas than for Burkholderia. So all of that's fine. We still have this somewhat slight deviation from linearity, and we're now going to look at models that again, an alternative way to express these relationships that try to capture this saturation effect with Pseudomonas. So we are looking for a model that fits our data better than the simple linear model. And let's review all of the models that we have at our disposal. So we can have a simple 2-parameter model that varies only with time. So we invoke that by saying this is the relative or the absolute abundance from qPCR data of the Pseudomonas bacteria, and this is time. And we end up with this simple 2-parameter model the only parameters are the slope or the intercept. So that's really the simplest model that that will give us anything, tell us anything about our data. And of course, when we do the analysis of variance, what we're comparing against is a model which doesn't even have a slope, which would only be the average of the log Pseudomonas data. We can increase the complexity of our model by considering the treatment category. Remembering there's 4 treatments in our data set, so each data point is at a particular treatment category. The background in the way that we've set this up is by the background is the treatment itself, and then we have the categories before treatment, recovery, and stable. So the in this case, this model assumes a constant slope. So we have these 4 regression lines, but they have a constant slope. The slope is going to be the coefficient of the coefficient that's assigned to the sample days column, right? That's going to be a constant slope. And then the background is the treatment. So these values here are the difference in the intercept between treatment and the other categories. So the difference in the intercept between treatment and before treatment, recovery, and stable. Those are the values on the intercept, and we perform inference. We can perform inference on each one of these individually, or we can perform inference by zeroing out all of them and ask whether treatment matters. So that's our 5-parameter model. So we can go from a 2-parameter model to a 5-parameter model. We can go to a more complex model, and again, these are, remember that the coefficient. Right, so we have an intercept coefficient. This is going to be the intercept of only the treatment categories of our background category. This intercept is going to be the intercept that's attached to time, right? So inference on that intercept is going to ask whether time is related to sample days. Each one of these dummy variables is related to a different category relative to treatment. So this is before treatment, recovery after treatment, and then the stable time point. And each one of these coefficients is going to be the difference between these, the difference in the mean of these different categories relative to the background, which is our treatment here. And we perform inference on whether B2, B3, and B4 are equal to 0. That's what the summary table does here. Or we can zero them all out and ask whether treatment makes a difference, right? So if these are all zeroed out, then our simpler model our reduced model is just the simple linear regression, and we do the analysis of variance to see if there's a difference in significance between those 2 models, and there is, with treatment being highly significant in that analysis. Right? Looking at the wrong direction. Again, we're zeroing out these B2, B3, B4 in this ANOVA to come up with this p-value here. So that's our 5-parameter model. We can consider our 8-parameter model. The 8-parameter model we can think of as having 4 independent lines. Right? And so we read this, we say there's a background to intercept, as before. So that's the intercept of our background of our treatment. Then we have the intercepts of before treatment, recovery, or stable. Right? So we do inference asking whether those intercepts are different for these categories than our background intercept. So that's 4 of our parameters: the background intercept and the 4 differences in the intercept. We have our slope of our background. Right? The slope of our background is here. But now, because there's an interaction term, we allow the slopes to be different as well. So for each one of our dummy variables, we ask, is the dummy variable different from the background? And for each one of these slopes, we ask, is the slope different from the background slope? Right? So that's 8 parameters, which we can think of as being 4 independent lines. Right? So when we go from the 5-parameter model to the 8-parameter model, we're dropping the assumption of a constant slope. So we have to have 3 more slopes. And that gives us our 8 parameters. And the 3 more slopes are here, and they're expressed in R as the difference between the slope of each one of these categories and the background slope. And again, we can do the analysis of variance by comparing the 8-parameter model to the 5-parameter model. And here, actually, when we compare the 8-parameter model to the 5-parameter model, that's what's shown here, that's not significantly different, right? So this model and this model did not explain a significantly different amount of data. So this is consistent with the lines with the 4 categories not having independent slopes. And when we look at the data, that seems reasonable, right? It seems reasonable here to think that these 4 colors, these 4 categories here, do not have independent slopes. So that seems consistent with our eyeballing the data. Treatment is under this analysis of variance from the 8-parameter model still significant, right? So we say that having the 4 treatment categories, although they don't have different slopes, they do have different intercepts. And again, that's consistent, right? It makes sense that the intercept of the red dots is less than the other, which is the background treatment category, is lower than the other conditions, right? So that seems to be consistent with again, just looking at the data, that treatment has an effect, and that is expressed as differences in the intercept. Okay, so but all of these models, the 8-parameter model, the 5-parameter model, the 2-parameter model, assume a linear relationship, and the argument was that maybe isn't the greatest model here, because the results, the data themselves don't seem especially linear, because there's the saturation effect. So can we make a more complex model that captures that saturation effect? That is to say, can we think about not lines but parabolas? So here is a 6-parameter model with 4 parabolas, all of the same shape, right? And we've invoked this now. So we invoke the 8-parameter model using the interaction term, using the star here, saying we want the interaction terms. We invoke the 5-parameter model with plus here, saying we don't want the interaction terms. We go back now to a plus here, so we're going to say we don't want interaction terms, but instead of having the fit be from a simple line, we fit it with a second-order exponential, that is to say from a parabola. So this is going to be parabolas without interaction terms. So we draw one parabola, which is our background parabola for treatment, and then we shift that parabola up or down by an intercept. Right? So now a parabola has 3 variables, right? Just a quadratic equation from our 8th grade algebra class. So these 3 variables are here as b0, b1 times x, and b2 times x squared, right? So those are 3 variables here. And then because there's no interaction term, there are 3 additional variables, which is just whether the intercept of this parabola, where the parabola hits the y-axis, is the same or not, right? So for each one of our 3 categories, we ask whether the intercept of the parabola is the same relative to the background treatment. And so we can move this parabola up and down just along the y-axis, and we do inference about whether the difference between the where this parabola hits the y-axis is different for our before treatment, recovery, and stable relative to our treatment background. So that's a 6-parameter model with 4 parabolas all the same shape. But of course, we could, instead of having a plus here, we could have a star. So we could say, let's allow the interaction terms. So let's allow the model to draw the best parabolas for all of the data. And that's going to be a 12-parameter model. And here are the 12 parameters here. So we have our 3 parameters that draw the background. We have our 3 parameters that draw the background. And then we have our 3 parameters that allow the intercept to shift up and down. And then there's 6 parameters that allow the parabolas to be different shapes, because you have 1 coefficient for each dummy variable that interacts with the x term, and 1 coefficient for each dummy variable that interacts with the x squared term. So we can do inference on each one of these 12 parameters individually using the summary statistic that R generates from the summary command, or we can do an analysis of variance here. And the analysis of variance basically says, hey, do we need these interaction terms or not? And of course, it's going to turn out that we don't need the interaction terms, and I'll come back to that in a second. But let's take another look at this 12-parameter model, just because this is pretty impressive, right? So we get lots and lots of parameters for not that much typing in R. So again, on the y-axis here is the Pseudomonas concentration as determined by qPCR. And this is the polynomial, our second-order polynomial, which is going to involve 3 parameters, because it takes 3 parameters to draw a parabola, which are b0 times the intercept, b1 times x, and b2 times x squared. So here are our 3 parameters that just have to do with time, that don't have anything to do with treatment, because it takes 3 parameters to draw a parabola. Then we have our first dummy variables that just move the intercept up and down, right? So we can think of this as the dummy variable times the intercept. So these 3 parameters just move the dummy variable up and down, and that does inference about whether the intercepts of these parabola changes. And then we have 6 parameters to move the shape around, because to move the shape of the parameter, you have to be able to move b0 or b1 or b2, right? So it's going to take 3 parameters to draw these three potentially different parameters to draw these parabolas that are here. Right? So another way to think of that is that it takes 3 parameters for each parabola. I have 4 parabolas, so I have to have 12 parameters. Right? Now, this is a pretty complicated model. What we can do in the ANOVA is say, well, do I need all these 12 parameters, or can I get by with the 6 parameters? Right? Do I need to have these 6 parameters here that allow me to change the shape of the parabolas, or can I just have the parabolas intercept the y-axis? And what this ANOVA value here says is, well, actually, if you drop these 6 parameters, you don't lose, right? The null hypothesis that you explain the same amount of variance dropping these 6 parameters, we fail to reject that null hypothesis. So we don't really need these 6 parameters. So we can live with this reduced model here instead of the full model that's there. And again, I think that's consistent if you just sort of eyeball the data, right? It kind of makes sense that there's that you can fit them with one parabola, right? It doesn't seem like the parabolas for the red dots, blue dots, or green dots have a completely different shape, although we're going to argue they do have a different intercept. So here I've just drawn each one of the, so I've drawn the model, and I've just shifted the model up and down relative to just the change in the intercept, and that's what's shown here from this fitted from the command fitted. This just says at each one of these points, show me where the model is, right? So show me y hat, where remember that y hat is the sum of this whole mess of these 12 parameters times the dummy variables. Okay, now what I've just said is pretty complicated, but in fact it's somewhat simplified because in fact day and day squared are highly correlated, and in general, as we'll see when we start to talk about PCA, you can't have correlated inputs into a numerical model, right? So if you think about a perfectly correlated, so if we go into paint here for a second, if you think about a model model that looked like this. The magic cards flash by for a second. If you look at a model that looks like this, B0 times x plus B1 times x2, right? So I have B0 x times x1 plus B1 times x2. If x, right, and we're trying to get a solution that minimizes the residual sum squares, right? So we want to minimize these errors. If x1 and x2 are perfectly correlated with each other, then there's an infinite number of solutions for b0 and b1. So if x1 and x2 are perfectly correlated, if I just double b1, right, if I just do double whatever I think b1 is, I can make 1/2 b0, and I'll get the same residual sum squared fit. So numerical models become unstable when the input variables are highly correlated. Well, x1 and x2 are in fact highly correlated, right? And so we generally don't want to be putting x and x squared, right? So if I look at the relationship between x and x squared, those are highly correlated. We generally don't want to be putting a highly correlated data into our models. So what does R do? How does R avoid the numerical instability by having time and time squared be correlated with each other? We can't fit them into the model. So what you noticed here, if we look at x time and time squared, I had this option raw equals true here, but by default, most of the time you would leave that off. So when you say linear model raw equals true, you get this relationship between time and time squared that looks like this. That's plots out like this. But if you leave out that raw equals true, so you drop raw equals true from your call to poly, and what R will do is it has actually rotated time and time squared onto a new basis, and this is actually very similar to what's going to happen when we look at PCA ordination coming up in 2 lectures, where PCA ordination is also going to be rotating our data into orthonormal bases. Right? And so R has taken that parabola and has rotated it around so that the correlation coefficient between the x and the y-axis is within round-off error of 0. Right? So we're in a new basis space now, where time and time squared are no longer correlated with each other. They've been rotated. The disadvantage of that, so this guarantees numerical stability in our model. The disadvantage is that time and time squared here have a very clear relationship, right? As time goes up, time squared goes up. Once you're in this new space, that's no longer true. So we lose our biological or our kind of intuitive understanding of what these columns mean by rotating them into this space where they have numerical stability. But by default, that's what you want to do. And as we'll see, this does not actually affect the inference of our models. We're still going to get very similar p-values once we've rotated onto our new orthonormal basis. So we invoke poly with the default parameters. We allow poly to rotate our time so that time and time squared are not correlated with each other to improve the numerical stability of our methods, and we get very similar results. Right? So when we compare the full model to the reduced model, we don't need the interaction terms, right? So these 6 degrees of freedom between the full model and the reduced model don't make a statistically significant amount of difference in the data. So we can go with our 6-parameter model instead of the 12-parameter model. Our 6-parameter model looks like this, much simpler than our 12-parameter model. We have our intercept. We have time and time squared rotated so that they're no longer correlated with each other. And then we have the dummy variables for the intercept that move the parabola up and down. And when we consider this model, treatment is still highly significant, right? So we can't go from a 4-parameter model to a 1-parabola model, right? The 4-parabola model to the 4-parabola model to the 1-parabola model yields a highly significant result. The change with time is still highly significant, but we don't need to draw 4 independent parabolas. We can draw 4 parabolas of the same shape and just move them up and down the y-axis. So that's completely consistent with what we saw with the linear model. We get very similar results for inference if we just consider the standard linear model, right? So if we go back to inference based on this model, here we get very similar results, right? So if we compare, it doesn't really matter whether we use lines or parabolas here. We get fairly similar results. And again, this is because the deviation from linearity was not so dramatic in our data. So whether we use the more complicated or the simpler model doesn't really matter in terms of the results. Both the treatment matters and time matters, whether you use the 5-parameter model with lines or the 6-parameter model with parabolas, right? And you can think again, the extra parabola, since the parabolas are constrained to be the same shape, the extra parameter just allows you to capture the saturation nature of the data, right? So the extra parabola says instead of extra parameter, since instead of drawing a line here, you can draw a parabola with one extra parameter to try and capture the saturation effect. But it doesn't really matter very much for inference whether you do that or not. So one of the great things about ANOVA, so I've said the inference relative to treatment and relative to time doesn't really matter whether you use the 6-parameter model or the 5-parameter model, but we can use the ANOVA itself to ask whether we can explain more variance comparing the 6-parameter model than the 5-parameter model. Okay, so here's the 6-parameter model, right? This is the model with the 4 parabolas all the same shape, right? So this model is this model here. That's our 6-parameter model. 3 for 1 parabola plus 4, 5, 6, right? So that's captured here. And it's captured by this poly 2 without the interaction term. So we can compare the 6-parameter model to the 5-parameter model, right? And the 5-parameter model was is this model, right? 2 parameters for the line, 3, 4, 5, right? So is this model a better fit to the data, 5-parameter model, or is it better to have 1 parameter that allows you to capture that saturation? Is the 6-parameter model better than the 5-parameter model? So we can use an ANOVA to ask that question, right? So we can say we can say here's the full model, here's the 6-parameter model, right? And here's so I just build that model and I get the residual sum squares of the full 6-parameter model, or I can build this model, which is the 5-parameter model, which are the 4 lines, right? 4 parabolas or 4 lines. 4 parabolas all the same shape for 6 parameters, or 4 lines all the same shape for 5 parameters. Which one's better? So I just build the models, I get the residuals. And then I grind through, right? The difference, there's 1 parameter difference between these models. And the full model has 6 parameters. So it has 124 degrees of freedom because there's 130 data points in the data set. So I grind this through and I do PF, and I get actually a very small p-value, right? That p-value is 2.3 times 10 to the minus 5th, which I can get manually here or with less typing here. Right. So even though it doesn't really make a difference in terms of the inference for the paper, in terms of treatments or in terms of time, the 6-parameter model seems to capture more variability than the 5-parameter model. Right. So we are capturing, when we have the 6-parameter model that allows the model to bend over to the data, we capture more data than a straight line can capture. And I think that makes intuitive sense because the straight line really has trouble, right? Drawing from here to here, it is not able to capture all of the data points that are up there. Okay. Now, there's nothing that says that we have to stop with a second-order equation. We can go to a third-order equation, right? We can just add another term, right? So this is now going to be b0 plus b1 to the x plus b2 x squared plus b3 x cubed plus the terms for the dummy variable. So we're adding one more variable to make this a cubic spline instead of making it a parabola. Right? And then we can use the same ANOVA approach to say, well, is this still a significant difference? And it is. So this 6th parameter or the 7th parameter made a difference relative to the 6-parameter model. So making this a cubic spline instead of making a parabola led to a better fit. And we can keep going. We can now make it a 4th-order polynomial to get a better fit to the data. And you're able to see here that we sort of capture more of the shape gradations of the data, and that still makes a significant difference. And we can add a 9th parameter to make it a 5th-order polynomial. And you can see it's getting smoother and smoother and smoother, right? We're smoothing out the curve by making the model more complicated, by making it more sensitive to the data, and that still explains a significant amount of difference. But now, when we make this a sixth order polynomial, adding the 10th parameter to the model, it doesn't make a significant difference. So using this approach, right, we get better and more refined models up until x to the sixth, right? So our curves here, right, our line doesn't capture very much of the data. This is our parabola. We're still not capturing very much of the data. There's still data that we're not able to capture as much. But as we go to higher and higher order polynomials, we're able to bend that curve a little bit more up, so it captures more of the data. This doesn't matter for the inference in terms of treatment type, but if you're looking for kind of a rational way to decide how many parameters should I have in the model, with 130 data points, I can afford the 10 parameters here, and this seems to be the best model overall. So in our fifth order model, right, in our model that has this exponential term including up to and including x to the fifth, right, we can use the simple ANOVA to show that we still don't want the interaction terms. So here we ask R to do an ANOVA on the full model including the interaction terms because we have the star symbol here. So what we're comparing here is a fifth order model without interaction terms. So that has the intercept plus 1, 2, 3, 4, 5 coefficients for the up to the fifth order polynomial. So that's 6 parameters plus the 3 dummy variables that reflect the shape moving this thing in 6-dimensional space up and down the intercept. So there's 3 dummy variables there, and that only makes for the 9 parameters. The full model with the interaction terms has these 9 parameters. Plus, for each one of the dummy variables, you have to reflect the dummy variable across all 5 exponential terms, right? And so that adds another 15 parameters. So you end up with a 24 parameter model. So we can ask R, do these extra 15 parameters here, multiplying each of the dummy variables times each one of these coefficients here, does that matter or not? And R thankfully says it doesn't matter, which means that we don't need the 24 parameter model. We can deal with just the 9 parameter model, which is already plenty of parameters. There's already enough complexity there. We don't get anything extra by adding these extra terms. In this 9 parameter model, we can, as always, just use the residuals, right? So the 9 parameter model is defined by this equation. This doesn't have the errors here. So we can look at the actual data points times the y hat. So this is y hat in this case from these 9 parameters. And we do that. We see that they're actually very well distributed. The assumption normality of those residuals is actually a very good assumption. We see very, very good residuals versus fitted curve. And when we do the KS test, we get a p-value that's much larger than 0.05. So these models certainly have some limitations, but we don't feel that one of these limitations is a violation of the assumption of normality.